All right, today's the 16th. Here's the problem. The function is x to the fourth, or the interval is 0, 4. We're going to find that c value in that interval such that f of c, this height, which is the average value of the function, okay, over that interval, times b minus a is equal to the area under the curve, okay? And we're going to try to find that c value, which makes this true. So we're going to find the c value where this is the case. Okay? Well, let's do it. F of c, now what would f of c be? That would be c to the fourth is equal to 1 over b minus a from 0 to 4. Our function is x to the fourth dx. So, we're looking for the c, where c to the fourth, that would be this height, is equal to 1/4. The integral of x to the fourth, x to the fifth over 5 from 0 to 4. Okay? That's 1/4. That would be 4 to the fifth over 5. That's 256 over 5. Oh boy. We're looking for that c value where c to the fourth is equal to 256 over 5. So c is equal to the fourth root of that thing. And the fourth root of 256 is 4 over the fourth root of 5. Gee whiz. I'm not sure how they want you to write it, but that would be the, oh wait, is that one of those that went to decimal, like 3 decimal places or something?
This one doesn't ask for decimal, just integral answers as a comma-separated list.
What?
Integral answers as a comma-separated list.
Oh, then something's not right. There's no list here. There's only one answer. Wait, what? All right, can you read the whole question right from the start?
Okay. Find the value of c guaranteed by the mean value theorem for integrals for the function over the given interval.
I did that.
Right.
But there's no list of answers. There's only one answer.
I know.
Asking for a coordinate,
Some may have more than one.
like plus or minus.
Like depending on what's happening.
Yeah, well, there's no plus or minus here because the interval is from 0 to 4. If they ask for a bigger interval, yes, it would be on the other side. There would be one as well, but they only ask 0 to 4. That should be the answer. Put that answer in.
Yeah.
Check it out.
Is c the x or the y?
C is an x value. If they want just the c, and I think that's what he said, this is the c value.
What do we want like in coordinates?
Well, it didn't sound like it.
Because it said an ordered pair, right?
Did it say ordered pair?
It said something pair.
No, it just said find the c value,
Yeah,
guaranteed.
that's
Yeah,
right.
it is right.
It is answered.
That's the way it is, so that's the way. You're thinking. That's good. That's good. All right, you got another one there.
Yes. The
Go ahead.
This one is f of x equals 4x to the third power minus 3x to the second power. The intervals are -1 and 3. And it's asking x comma y.
Okay. X comma y. Yeah, read it just to make sure we know what we're doing here. Find x comma y. That's the ordered pair.
Average value of the function over the given interval and all values of x in the interval for which the function equals its average value.
Okay. All right. So it is possible in this one there are more than one. There are several.
This one's asking round zero answer to 3 decimal places.
Oh, man. Who assigned these problems? What the heck? Some jerk. Right. Holy moly. All right, let's take a look at this thing. Oh, what I'd like to do is take a look at the graph of this first here. Let's take a look at this graph here. I'm going to factor out an x squared. The graph of this is like this. Okay. It's got a 0 at 0. It's got a 0 at 3/4. Actually, it's got a double 0 at 0. So the graph of this function looks like this. Okay, this is 3/4. And this is 0, 0 here at the origin. And the interval is from -1, oh boy, to 3. Okay, so there could be several values here. We're going over this interval from here to here. So it's certainly possible that we get more than one answer. Okay, is everybody okay? Okay. Okay, so let's do it. We want to find the C value and the f of C value. Okay. All right. Let's find the average value first. The average value is equal to 1 over b minus a from -1 to 3, 4x cubed minus 3x squared dx. The average value is 1/4, 4x to the 4th over 4, 3x cubed over 3. Well, that's not bad then. That's decent. So we get 1/4. Am I still on there? Yeah. 3 to the 4th, 81, minus 27, okay? Thanks. 54, minus 2. Wow, thanks. Okay? That's 52 over 4, which is 13. 52 weeks in a year, 4 seasons, 13 weeks in a season. There you go. Or decks in a card, 4 suits, 13. All right, anyhow. So we got an average value of 13. So here's what, I see trouble lurking around the corner here. So what we want to do is find the value of C in this interval that makes this function equal to 13. All right, is everybody okay with this?
So it's going to be the original equation?
Yeah, we want to know, okay, we know we want to find out where this function is equal to 13. Oh, there's only going to be one. It's way over here somewhere. That's equal to 13. The average value is way here, but I don't know what it is because I got to solve the stupid cubic here. All right, well, that's all right. We'll figure it out. All right, so what value of C gives me a function equal to 13? Is everybody okay with this? So we want to find C where the value of the function at C, which is 4c cubed minus 3c squared, is equal to 13. So we want to solve this. 4c cubed minus 3c squared minus 13 equals 0. This is probably irrational because rational root theorem says the only possibilities I have are 1, -1. Those aren't working. 13, -13. 13 halves. 13 fourths are the possible tries. This is something you should do in Mathematica, okay? This is, you gotta, can you solve it on that?
Oh, I already did.
You did? It's a cubic?
It takes 2 seconds.
Go ahead. No, I want you to read what the answer is.
X
C
equals 1.778.
1.778. Thank you. Wow. 1.778. Now, I must say, it's not, off the top of my head, I can't see how to factor this. You do have possibilities. There's rational root theorem that says you've got some possibilities to try. You can try with synthetic division. Like I said, 13 doesn't work. 13 over 1, 13 over 2, 13 over 4. But none of those, that's not 13 over 4, is it? Oh, what's 13 over 4? No, that can't be it. So it is an irrational answer. They would expect you to use a computer algebra system or something in order to solve the cubic polynomial. Mathematica would do it. If you were to do an n solve, which would be perfect here, this is what you would do in Mathematica. Yeah, the syntax would be this. You got to use double equal signs here. Okay. With that, in Mathematica, it would give you 3 possible roots, okay? 3 possibilities. Only one of them is probably going to be anywhere close. Actually, the others may be imaginary. So there's only one that's real, one real root. All right, so that's what you'd have to do, though. Okay. All right, any others? That's it. Okay, ready to go on? We got a few things to do. Here we go. First thing we have to do is to generalize the inverse trig functions. What does that mean? Well, that means this. Right now, we have the integral of 1 over 1 plus u squared du is inverse tangent u. We have that. That comes about directly from the from Calc 1. Okay, the derivative inverse tangent 1 over 1 plus u squared. We want to generalize this. In other words, what we want to be able to do is things like this. Okay. Well, we have two choices. One, we can generalize it so we have a general rule that will take care of things like this for us, so we don't have to do anything but apply the rule. Two, we can keep with what we have and be prepared to derive, go from here to here every time. What I'm going to suggest that we do is we're going to generalize this and we're going to do the generalized rule. You may choose not to. That's your decision. But just be prepared when you see this on the test. You're going to have to go from here to here, okay? So your choice is to memorize a slightly more complicated rule than we have right now, or be prepared to derive it when you do the problem, okay? That's typical math. You can decide to learn a very small list of things, memorize a very small list, but be prepared to derive everything else, okay? Or know a real long list of things and be prepared to derive very little, okay? It's like 2 to the x. You can choose to memorize that form, a to the u form, or be prepared to derive it by using logarithmic differentiation. And in my opinion, it doesn't come up often enough to memorize the more general rule. You should be able to just do it, derive it. You understand what I'm saying here? You see what I'm saying? All right, these, however, I think you should know. If you're going to take differential equations at some point, you definitely should know the more general rules, because in differential equations, you're going to be doing these kinds of integrals a lot, okay? If you're not doing differential equations, it's not a big deal probably, okay? Calc 3, we don't do it that often. We don't do these integrals. But diffie-qs you do. So if you're a double E and need to take diffie-qs, definitely. Mechanical, do you have to take diffie-qs mechanical? Probably. No? Minus? No?
I don't think so, though.
No? Wow. And the computer science engineers now, they are changing that whole curriculum around. So, well, you should know what you're going to have to take. So here we go. Let's do one in specifically, this one, and then we're going to generalize it, okay? Now, we want to go from here to here. What are we going to do? I'm going to take a 9 out. Now, when I take a 9 out, I can't just rip the 9 out of this 9. I have to take the 9 out of this x squared. And what you should do is consider this as 9x squared over 9. Take the 9 out and be x squared over 9. Okay. Now, this is 1/9. This is x over 3 squared. Well, that's this form. What's u in this case?
X over 3.
X over 3. Very nice. The du then is, du dx is 1/3, so du is 1/3 dx. And we can do that. That's not a big deal. I can multiply by 1/3 and multiply by 3. So we end up with 1/3, the integral of 1 over 1 plus u squared du. We have this form. That's equal to 1/3 inverse tangent u x over 3 plus c. Okay?
On the,
Go ahead.
On the, I guess like the first first line there, the over at the end, you have 1 over 9 times 3, and then 1 times 1/3. Where's the 3 from?
This 3 comes about because I had to multiply by 1/3 so that I could get my du, 1/3 dx. So I had to multiply this by 1/3 in here and by 3 outside to compensate.
Oh, okay.
Okay? So I'm multiplying by 1. Abby?
So can you not do this if you don't have like a square added to it? Like if it were 1 over 8 plus x squared, can you not do this?
All right. Okay, everybody else up with this?
Can I just see the sheet?
What's that?
Can I just see the sheet?
Can you explain where the 1/3 came from?
All right, wait. All right, hold on a second. Okay, let's go ahead, Lewis.
The 1/3, where'd you get that?
This 1/3.
Yep.
Okay. What I'm trying to do, hold on, Abby. I'm getting to you. I'll be there. Okay. What I'm trying to do is take this integral that's given and rewrite it in this integration form that we have. This is what you should be doing for all the integrals that you get. Here's the integral we have. Here's what we want to be. We want to be here. That's the integration form. I can do that if I can get rid of this 9. I can get rid of the 9 by factoring out the 9. 9 plus x squared. Think of it this way. And I got a common factor of 9 that I can take out of each of these. Okay. That 9 right here comes out front. Okay. There's my 1 plus x squared here. By doing that, this is my u squared, x squared over 9. U then is x over 3. Okay? That's what this is. This is saying, okay, I have this form where u is x over 3. What is my du? My du is 1/3 dx. Take the derivative of x over 3, that's 1/3 dx. Okay? I don't have 1/3 dx. I don't see it there, but I can get it by multiplying by 1/3 and by 3. What have I done? I've multiplied the integral by 1/3 and I've multiplied by 3. I've multiplied it by 1. That's okay. That 3 I can take out front. It's legal to take constants out front. Okay? Why did I do that? Because I wanted to get this form. In order to get this form, I had to have 1/3 dx so I could replace it with the du that I needed. And that's what I did. This 1/3, okay, gets multiplied by 3. There was a 1/9 out there. Times the 3, that gives me 1/3. Okay? This is the integration form. And I mentioned this last time. I strongly recommend that when you're doing these integrals with these u substitutions, that you take the time to write this step where you actually write the integration form that you're using. Okay? This is it right here. Now, what is that form? That is inverse tangent u. U is x over 3. That's the answer. Okay? That is the answer. That is the integral. Abby.
Like, that only works because you had, so say you had like on the bottom 8 plus x squared and then you took out a 1/8. So then
Okay, give me an example of what you want me to do.
Like the same thing but 1 over 8 plus x squared.
1 plus 8? Oh, like this? Oh, yeah, you still take an 8 out, but it's not as nice.
Okay.
Okay, because now, now it's 2 squared to 2.
Yeah.
Yeah, yeah. Yeah, not even an 8. If that had been a 3 or something like that, you get a square root of 3 in there.
Yeah.
Let's do it with the 8. So if you take the 8 out, square root of 8 is 2 squared to 2. Yeah, so I'll just write it this way. This is your u now. X over 2 square root to 2. You would multiply by 2 square root to 2, okay? 1 over 2 square root to 2, or 2 square root to 2, and divide by it. Same way we did before, but now it's...
So it still works.
It still works, yeah. Yeah. Okay? How's that look? Now, you can be prepared to do this little derivation thing, which isn't that bad. Or we can go to an a squared plus u squared form and memorize the more general form so that we have this immediately. Okay? And we don't have to go through that. Let me show you what I'm saying. I'm saying this. Let's suppose we have this integral to do. Okay? This is the generalization of the inverse tangent form that we already have. Okay? What I'm going to do here is take out, what am I going to do first? I'm going to take out what?
Probably the A, because you have U.
Even the, not just the A.
The U.
No,
A squared.
the A squared. I'm going to take out the A squared. This is going to become U squared over A squared du. When I multiply it through, I'm going to get what I started with. Now, consider this as 1 over A squared okay? Now, this is an integration form. I've already used the letter U. I am now going to use the letter V to generalize this. I'm going to let V equal U over A, okay? dV is 1 over A du. I need to multiply the numerator by 1 over A and multiply outside by A, just like I did with the 1/3, playing the same role to get 1 over A, integral of 1 over 1 plus V squared dV. That 1 over A du is the dV. This is the integration form that we have. We have 1 over A, inverse tangent, V, or 1 over A, inverse tangent, U over A, plus C. This is our generalized inverse tangent form. Okay? Please note, that's what we got for the last, when we did that last example. Okay? So if you've memorized the generalized form, you look at this and say, ah, A is 3. This is A squared. A is 3. The answer, therefore, is 1/3 inverse tangent x over 3 plus c. You go immediately to the answer without having to go through and complete this and do this what we did. Okay?
You just leave it.
Yeah. Which one? This the new one here?
Yeah.
Okay. Now there's one more thing with this. There's another thing we can do here. Let me just show you this here. I'm not even sure they have any examples with this, but you may. Let's suppose you had something like this. We're going to deal with such things, not next chapter, but the chapter after next. Okay, the third chapter that we cover in techniques of integration. But I do want to point this out now, just in case, of course, my math WebAssign throws something like this at you. This is not of the integration form that we just did. It's not the right form. There's a 6x thrown in here. But there is something you can do to this to get to that form. And that is to realize that if you made this a perfect square, adding 9 to that x squared plus 6x makes it a perfect square. I can't just add 9 because I feel like it. I'm going to subtract 9 as well. Okay. I'm going to add and subtract 9. Why? Because that gives me this. And guess what?
Same form.
We have the same form. It's 1 over u squared plus 1, or 1 plus u squared. U in this case is x plus 3. du is dx. I don't even have to do anything. Okay. What I get for an answer is the inverse tangent of u plus c. Okay. I just want to point out that possibility of completing the square there. Okay. Okay. This is the inverse tangent generalization. 1 over a inverse tangent u over a plus c. We have 2 to go. You ready? Let's do the inverse sine generalization. Okay. Be okay with this? You guys all right? Wait, moment. You're all ready? You ready? Okay, let's do the inverse sine one. I'll tell you, let's just do it. Here's the problem, is to integrate 1 over the square root of a squared minus u squared du. I just, as a note to bene here, the integration form we have right now is 1 over square root of 1 minus u squared du is inverse sine u. Okay? That's what we have right now.
Can you just pull that paper down just a smidge?
What's that? Like that?
Yeah, the record thing is there.
Oh, yeah. Okay. Good call. It's the way. Okay. I want to generalize to this form. So instead of 1 over the square root of 1 minus u squared, if I had a 9 or a 16 or even a 7 or an 8 in there, we could still do the integral. Now, again, you could choose not to do the generalized form, but be prepared to take something like this and get it into this form, okay? You could do that. I don't really recommend it, though. Okay, you ready? Here we go. What's step 1? What are we going to do first? What do you think we should do?
Get rid of the square root?
I can't. It's there. Can't do it. Can't get rid of it. It's just stuck there. Just can't do it.
And you couldn't have like a, let's say we used v again, you couldn't have a dv under that square root. You couldn't bring it outside of the square root.
Bring what outside the square root?
If you did like the u substitution and you had a dv, you couldn't put it under the square root. It had
No.
to be.
No.
Okay, I'm just,
But there is something I can do here.
so would it split it up?
No, don't even think about that. That's illegal. That's not good. Math gods are a little bit angry right now, okay? So don't even suggest that, okay? I don't want my car to be gone when I get out there because they lifted it out of there and threw it somewhere.
Pizza next week at Math Club.
Yeah, that'd be
like
bad.
righteous
That'd be
here.
bad. I know. All right. Anyhow, what do you think? Any suggestions for what we should do first? Here's what we know. Here's what we have. We'd like to go from here to here, but I am going to use a v. I'm going to end up having to use a v. But how do I go from here to here? What am I going to do first?
Get rid of a.
Yes. I'm going to get rid of the a. I'm going to take the a out front. Okay? So let's do it. I can take the a out of the square root. I'm not sure that's what, I don't think that was what you were saying. But I can take an a out of the square root. Now watch this. Here, just first of all, let me factor out an a squared out of each of these. Okay. When I multiply this through, can you see that all right? Is that okay? Mohit, you can see that? See? Okay. I get what I started with. Now, I can take the square root of a squared out front. What is the square root of a squared? A, we're going to assume a is positive. Technically, it should be an absolute value, but we're going to take it out and assume a is positive. That's what I have right now. I want to get it into this form. I can get it into that form by letting v equal what?
U over.
You bet. Nice.
Now, how did you get the u squared over a squared?
I wrote u squared over a, oh, right from here?
You just did like sort of derive the.
Yeah, what I did, if you think of u squared as a squared u squared over a squared, and then take the a squared out, you get a u squared over a squared left. No, that's not good. It's what I did before with tangent. It's the same thing. Here, do you realize when I multiply this through, I get what I started with?
Okay, because the a squared cancels.
A squares cancel, yeah.
And then you just have 1 minus.
Then I have a squared minus u squared, which is what I started with. So,
Yeah, oh, okay.
Okay.
Yeah.
Okay. Okay, now I'm going to let v equal u over a. dv is 1 over a du. I could move that back inside. There's my 1 over a, but I'm not going to do it that way. What I am going to do is multiply by 1 over a and by a. Okay? A's cancel. I have 1 times 1 over a du. That's my dv. So I have 1 over square root of 1 minus v squared dv. Okay? That's the integration form that I have. Please note, in the inverse sine form, the a's just cancel out. In the tangent, there's 1 over a still left there because it comes out as an a squared, not as an a. Okay? So, what's the integral? This is inverse sine. V. But what's v equal to? U over a. And there we go. That's my generalization of the inverse sine. Okay? So, if you had this, integral 1 over square root of 17 minus x squared dx. And web assign may give you something like this. What is the answer to this? What is this integral equal to?
Is it going to be 1 over the square root of 17 arc sine?
No, because there is no 1 over a out front here like there is for tangent. But you're close, but there is no 1 over the square root of 17. What is the integral equal to?
That's in sine?
It's inverse sine of
1 x
x over,
17.
Square root of 17.
what is it?
Square root of 17.
Square root of 17. That's your answer. Why? Because what do we have here? This is my a squared. A is the square root of 17. U is equal to x. The du is dx. I don't even have to multiply by anything to get it. Okay? I have the form directly. Okay? A squared minus, well, v squared in this case. Okay? That is the answer right there. U is x, a is the square root of 17. That's what you need. Is everybody okay with this?
So then this is the general rule.
That's
You're
it.
saying
That's
it's
it.
longer, but if you memorize sort of these forms.
That's correct. If you memorize that form, you don't have to take a 17 out as the square root of 17. You don't have to get an x over 17 quantity squared. You don't have to let u equal x over 17 and the du 1 over 17 dx and multiply by 1/17 and by 17. This is the answer immediately. That's what I'm saying. Okay? Man, I'm already working like a dog. All right, you got one more to go. Here we go. I would not give you this one on the test. Inverse sine, inverse tangent, yes, it's possible. But the secant one, I probably wouldn't give you. It just doesn't come up often enough to warrant it, but I am obligated. I have a responsibility to show you this, and I am going to do this, okay? It's on the syllabus. We're going to do it. So here we go. Right now, we have this integral. This is inverse secant u. You either have the absolute value here or here, believe it or not. Okay? Because of the way inverse secant is defined. Okay? If you don't have it here, you have to have it here. That's what we have right now. What do we want to do? What do I want to do? Let me clarify. Let's be more accurate here. What do I want to do is to do this. Okay? We want to generalize to u squared minus a squared. Okay. What do you want to do first? That's correcto. Nice. I'm going to take out an a squared from each of these. It comes out of the square root as a square root of a squared. It comes out of the square root as an a. I'm going to assume that a is positive. I'm going to take it all the way out front. Here's what I have right now. That's what I have right at this instant. All right, we got a little problem here. The little problem here is this guy in the front. In order to do the integral and get it into the right form here, what am I going to let v equal? What's v equal to in order to get it into that form that I want, which is this form here?
Now, I guess this,
U over A.
U over A is correct. That's totally correct. That's exactly what the v has to be, is U over A. The problem is I don't have the U over A here, and I want to make this a v, so I'm going to have to divide by A and multiply. Go ahead, Dylan.
if you set v as a over u and then raised it to the negative 2 power, that would,
You got problems. There's problems.
it wouldn't reciprocate back to the same thing u over a if you raised it.
Well, it would be, but why would you want to write it that way?
I had a thought.
Well, having a thought is
I
good.
didn't know if it was.
Okay, having a thought is good. It's just that seems to be making it a little bit unnecessarily complicated. What we're going to do is let v equal u over a. Okay. The dv is 1 over a du. There's a couple things I have to do here now. One thing I have to do is get this 1 over a here and multiply by a. But there's another thing I have to do, and that's to get this as u over a so I can replace it with v, so I can have this right, the form here. So I'm going to have to divide this by a here, and that means doing what? Having another 1 over a over here. This is going to be an 1 over a squared. I'm dividing the denominator here by a. I also have to multiply the denominator by a to compensate. So these will cancel. Okay? Yeah, no, yeah. It's like if I had this, and what I wanted to do, no, it's not like I had this. Yeah, forget that.
So did you factor out an a squared? Did you
I factored out an a squared as an a when it came out of the square root. That's the one of these. This a comes about because I had to multiply by 1 over a to get my dv. But I have another a down here because I had to divide this by a so I could replace this thing by v as well. So when I divide that denominator by a, I had to also multiply the denominator by a to compensate. When I clear away everything, what I'm ending up with is 1 over a, the integral of 1 over absolute value of v. I'm going to make this inside the square roots, v, it's this, square root of v squared minus 1 dv. Hopefully you can convince yourself that all this mess is the same as this, what I have right here.
Now, aren't you only taking the absolute value of u and dividing it by a? And
Yes.
in the b step, you're taking the absolute value of the both parts.
All right, say it again now.
It's absolute value
Of u, and I'm dividing it by a.
And then with the v substitution, you take the absolute value of that entire fraction.
This v substitution of let v equal u over a. See, absolute value of u over a is the same as absolute value of u over a. I'm assuming a is positive when it comes outside the square root. Hey, Chris, you made it. Okay? When it comes out of the square root, we're assuming a is positive. Okay? So absolute value of u all over a is the absolute value of u over a. So, we can do it. Chris is here. This is good. Okay. I've got notes for you and what we've done. We've been generalizing the inverse trig functions. So here we go. We have 1 over a, inverse secant, v, because that's what we have right here. That's the integral. That's exactly what the integral is. Inverse secant u, v, doesn't matter. But what's v equal to? U over a. So, now I'm going to rewrite it. I'm going to rewrite it on the next page. Wait, I can't be running out of paper already because we have a long ways to go. Okay, you ready? I was only kidding. We got plenty of paper here. Okay. Whoa, Jimmy, how you doing? Wow, what a good thing. Yours is here. This is good. Okay, so here's what we have. I'm going to summarize the three things we've already done. Okay, the last thing, the one we just did was to do this. We just generalized the inverse secant form for this. Everybody all set with that? Okay, so what we have is this. The integral of 1 over absolute value of u, square root of u squared minus a squared du is equal to 1 over a inverse secant u over a plus c. That's what we just derived. The other two we did are these two. The integral of 1 over a squared plus u squared du is 1 over a inverse tangent u over a plus c. And the integral of 1 over square root of a squared minus u squared du is inverse sine u over a plus c. Those are the three generalizations we did of the three inverse trigs. Now, you may ask, why not the other three, Burns? Okay? Why not do inverse cosecant and inverse cotangent and inverse cosine? I'll tell you why. They're never used. Why are they never used? The inverse cosine is this one. It's got a negative one there. But if you had to do this integral, guess what? You take the negative out front, and you do this. You never need the inverse cosine. Okay? Why does that work? Because there's a rule. There's a trig rule that says inverse sine x plus inverse cosine is equal to pi over 2. So, one is a constant minus the other. So inverse cosine is a constant minus inverse sine. But this constant plus that constant is a constant. So you never need the other three. It's only those three that I gave you. This one, and this one. Okay. Okay. How are we doing? You okay? Some of you guys seem sad. No? Okay, good. All right. You sad, Dan?
No.
Dylan's never sad. Dylan's never sad. Devin, you're never sad, are you?
Sad they beat me 4 times a week.
Oh, just don't be sad over that. You should be happy it was only 4 times. All right. All right. Let's go on. Are you ready? Let's go on. Wow. Yeah, maybe it won't be that bad today. Here we go.
Just to clarify, that
Yeah.
pretty much rounds out 5/8, right?
Is that 5/8 inverse trig functions?
Oh, I assumed you.
I don't know. I don't know how the individual sections go. It could be 5/8. I really don't know. Wait, who's got it? Somebody has WebAssign. Chris is on it. Chris has already got it. We would need to know, Chris, if 5/8 is the inverse trig functions on WebAssign. It doesn't matter. Let's say yes. Yes. Okay. Okay.
Yeah.
It is? Yeah, thank you. Then let's do 5/9. Here we go. 5/9 is on the hyperbolic trig functions. Whoa, man, this sounds cool. And actually, there are a class of problems for which the solutions are forms of the hyperbolic trig functions, okay? There are two that we are concerned about, and that is sinh, okay? X, that's sinh x is how it's pronounced. It's the hyperbolic sine of x. It's equal to e to the x minus e to the opposite of x over 2. Okay. When you study hyperbolas in conic sections in Calc 3, the sinh function can play a role on the hyperbola. They're called the trig functions because they have properties very similar to the trig properties, but they're either identical to the trig properties, like sine squared plus cosine squared equals 1. That's a Pythagorean theorem for the trig properties. For the hyperbolic trig functions, it's sine squared plus cosine squared is not, it's not plus equals 1. It's sine squared minus cosine squared is equal to 1. They're always off by a sign, okay, S-I-G-N. They're off by a sign. They're very similar. Some are exact and some are not. All right, we don't need to do that. I do want you to know that sinh is equal to e to the x minus e to the opposite of x over 2. If you do the graph of this thing, here's e to the x. What's the graph of e to the opposite of x look like? What's that graph look like? How does that graph differ from this graph? How does replacing x with its opposite change the graph? What does it do to a graph when you take a function and its graph and then replace x with its opposite?
As it reaches, as it goes towards like -1, it's really high, but then as it keeps increasing, it is almost to 0.
Yes, that's true. And how is it related to this graph? Replacing x with its opposite? What's that?
Symmetry among the y?
Yes, exactly what it is. Replacing x with its opposite gives you a graph that's symmetric. These two graphs have symmetry with respect to the y-axis. And what happens if you have a function and you replace x with its opposite and there's no change in the graph? Then what? What do you have then? That's exactly right. An even function, okay? That graph must have symmetry with respect to the y-axis because replacing x with its opposite causes it to flip around the y-axis. And if there's no change, it must have been symmetric with respect to the y-axis. That's the characteristic of even functions. Okay, so e to the x, e to the opposite of x. What does the sinh function do? It takes their difference and divides by 2. If you take their difference right here, this is the point 0, 1. If you take their difference, where they're equal, that's 0, and divide by 2, you start here. I'm going to make an asterisk for the hyperbolic sine function, the sinh function. As x increases, taking the difference between these two, looks more and more like e to the x, because this guy is decreasing to 0. And then we're going to divide that by 2. So as you get away from the origin, the graph is looking more and more like e to the x over 2. Take half of that. So it goes up like this. It goes up like this here. It's halfway up this thing, this side. Okay. Now, on the other side, if you take e to the x, that's this guy now, minus this guy, what do we get if you take this one minus this one now? What happens there? Where are we? Positive, negative, or 0?
Q3.
Q3 is exactly right. We're in negative territory. We're taking smaller minus bigger. So what happens is it looks like this. Okay. It looks like if you take this minus this, you're going to get negative, and it's going to be half of that. So it looks like this. Okay. This is what it looks like. We don't care, really. That's what it looks like. Okay. The other one is cosh, hyperbolic cosine, e to the x plus e to the opposite of x over 2. This one is more important as far as applications go. Actually, there are many applications of cosh. If instead of subtracting these two and dividing by 2, I add these two and divide by 2, okay, what happens is I get a graph that looks like this. Okay? Add these and divide by 2. When I add them, I'll get up to here to 2, and then, okay, so it's right here. Okay? And what it looks like is this. This is cosh. Okay? That's what it looks like. Gee, just by looking at it, what kind of function do you think cosh is? It's not a, it looks like a parabola, but it doesn't have the same properties. But it does look like a parabola. But what kind of function is cosh?
Even.
Thank you, Dave. Even. Okay, it's got the symmetry with the y-axis. What kind of function do you think sinh is, just by looking at it? Odd. What kind of function is sine x? Odd. What kind of function is cosine x? Even. Yeah. See, there's similarities there. Okay. Cosh, cosine, both even. Sinh, sine, both odd. Okay. Odd functions have symmetry with respect to the origin. Okay. Even functions have symmetry with respect to the y-axis. What is an application of cosh? Well, Dylan said it looked like a parabola, and it does look like a parabola, but it doesn't have the same properties. Well, actually, if you take two telephone poles and string a wire between the two, that wire will have in the form of a hyperbolic cosine function, not a parabola. It has the properties of cosh, not of an x squared. So and those are important. If you could come up with a way to stretch that wire and minimize the distance, so you get some wire that's practically straight across, and shorten the distance and save a lot of money on wire, you'd have something, okay? And actually, there are engineers that's what they work on. Of course, having wires up above the ground like that is kind of silly. We're all going to be wireless anyways, right? Just everything's going to be wireless at some point, I think.
They already have like wireless charging and stuff too.
Yeah, that's the rumor for March 15th. Apple is going to come out with wireless charging on the
They
phones.
already have that.
Yeah.
For Samsung, yeah, the edges and stuff.
Well, it's like the charge pads,
The
but you have
Qi.
to have like the certain
Qi.
case on your phone, and then
They haven't built it in. And
I tell-
there's a TED Talks too, where
So there's just a
this
battery
guy
cover.
just came to
What's
wall
that?
and
So, like, for the
powered
back
television,
cover,
his phone up
there's
and
this, like,
charging too, so it's
It's like a magnetic field that's
Yeah.
created. And then there's like a circle thing. There's also a magnetic field,
Probably
so it
not
just pretty
much
much
more.
works like a
stand in
Really?
front of it, get charged, and you
transformer.
can sleep
But
anymore.
the ratio's like 1-to-1 pretty much.
Cool.
People
This
talk about
is-
like cell phones and stuff.
This was Nikola Tesla's dream, right? Tesla, what he wanted, he envisioned a world where you had energy, free energy, instantaneously all over the earth, where you could just tap into this free energy source. And that's what he was working on. And it was one of those problems that he just couldn't solve completely. And he went crazy, like Nash did with his math and other people have done. He ended up, poor Tesla, one of the greatest minds of the 19th century, just ended up feeding pigeons in Central Park. That's what he ended up doing.
They added up the like patents and stuff he lost, if that was true, and it was like billion. Some people said trillions of dollars, but it's like billions of dollars.
Yeah. Everybody took his patents. He was a very generous guy. He was naive when it came to business. And
like
GE guy. Who was the GE guy?
Kettering? Or no, it's GM.
Somebody.
I
He
know
just
what you're
used
talking
just
I know
used
what
them
you're
all up.
talking
Yeah. Anyhow, but that was his goal. He envisioned this circling the earth, this grid of free electronic energy that everybody could just tap into. It was, well, maybe we're getting there. Maybe slowly, I guess. We'll get there. You guys will get there. All right, cosh. What are we going to do with cosh and sinh? Not much. Let's take a derivative of sinh. Let's find the derivative. Okay. So we have to take the derivative of sinh. The derivative, the way to do this derivative is break this up into two parts. What's the derivative of e to the x over 2? I'm breaking this up into two parts. Here, let me rewrite it. Okay. What's the derivative of e to the x over 2? Thank you, Jim. Minus, what's the derivative of e to the opposite of x over 2? times?
No, like negative.
Yeah, exactly. So the derivative e to the opposite of x, okay, or negative x over 2, is e to the negative x over 2 times a negative 1 times this minus gives it a plus there. Well, what's this equal to? That's cosh. In a way. Now you're speaking. That's a way. All right, that's cosh, okay? So the so the derivative of sinh is cosh, okay? Derivative of sine, cosine. Nice. Let's do cosh. Take the derivative. Derivative of e to the x over 2 is e to the x over 2. The derivative of e to the opposite of x over 2 is e to the opposite of x times a negative 1. And what is this equal to? Sinh. Oh, that's too bad. Because here we go. This is what I'm talking about. The derivative of sinh is cosh, just like the derivative of sine is cosine. But the derivative of cosh is sinh. Unlike the trig function, where the derivative of cosine is negative sine. I know it. So there's one that agrees totally, and the other one is off by a sine. Okay? All right, those are the two derivatives. They give rise to two integration forms. Okay, you ready? So the integral of sinh. Okay? Now, if I'm going to integrate sinh, integrate this, what is the integral of sinh? What function has a derivative equal to sinh? Cosh. Okay, that's the way. Okay? Because the derivative of this is this. I'm going to generalize it. Here we go. The integral of sinh u du is cosh u plus c. Okay? That's one more integration form that we have. And the next one I give you, I believe, will be our last integration form. So this is cool. So the integral of cosh is sinh. Why? Because the derivative of sinh is cosh. The integral of cosh u du is sinh u plus c. Okay? Two more integration forms. So, on the test, what could you possibly see? There's no room for, I'm not going to give you any derivatives, but I will give you an integral like this. What's wrong? Devin, what's wrong?
Nothing.
That was not your nothing wrong face.
No,
Oh, you were thinking of something else. Oh, okay, never mind.
I'm actually, my eyes are straining a little bit.
Oh, they are? Should I rest? Should we turn the lights off?
No, we're good.
Okay. All right. So, what you may see on the test is something like this. The integral of sinh 3x dx. Okay. This could be a test question. What form is this? What's the integration form here? What's the integration form?
Sinh u du.
Thank you. Thank you. Sinh u du is exactly what it is. What's u?
3x.
Very nice. What's du?
3d.
3dx, yeah. I don't have a 3dx, but I can get it by multiplying by 3 and by 1/3. I now have 1/3 the integral of sinh u du. There's my integration form. Check it out. Make sure that makes some sense. Okay. Egg, you all set there? Louis, you all set? You all set?
Can you just leave it up for a little?
I can. Jimmy, you all set? Good man. Sam, you all set? Dan?
Yep.
Carissa? Is it, that's it, right? Carissa, okay. I got it. Okay. And that's equal to 1/3 Integral of sinh is cosh. U is 3x. Let's see. That's the answer I'll be looking for. Okay? Well, I'm going to tell you, that's the hyperbolic trig functions. Whoa. Did you guys already do those before? No, you didn't, huh? You did not. Okay. One more thing to do, and that's in chapter 6 now. We do one section in chapter 6. What's that? I can't hear.
Radioactive decay.
Yes, and population growth. We'll do population growth first. This is 6.2, I believe. Whoa. Yeah, population growth. And radioactive decay. Okay. Population growth models are being researched even as we speak. What we're going to do is the simplest possible population growth model. One that is useful over short periods of time, okay, very short periods of time, which is not useful, however, for making predictions long term. It is useful if you have bacteria, say, in a petri dish in a lab, and you can predict how many bacteria there will be after a certain number of hours. Okay? But it's not useful to predict over an extended period of time, like I said. Okay? It says this. The population growth, this is an exponential growth model. Basically, it says this. The rate of growth of a population with respect to time, how fast a population is growing, is proportional to the population at any given time. Okay? It also says at t equals 0, the population is the initial population, whatever that happens to be. This k typically is a percent. If you have a population of Staphylococcus growing in your throat at 5% per hour, okay, that's compounded growth continuously. It's a continuous compounding. It's exponential growth. Okay? Oh, let's do it. Let's suppose you do. You got a Streptococcus, strep throat. Yeah, Streptococcus in your throat, and they take a culture and they find that you have, let's suppose you have, I have no idea, is it 10,000, a million? I have no idea how many of these little critters would be in there to give you strep throat. Does anybody have any idea?
I mean, millions. Would probably
Millions, maybe, huh?
Millions, you would be sick. So
Maybe you'd be dead, though, if you had millions of them. I don't know.
You have billions of cells. So
I know,
I
but
think of
millions of
the width of a-
strep
The
cells?
width of a cell, I think, is roughly the 1,000th of a human hair. I think, like offhand.
Oh, it's probably your hair. My hair is so thin now, and that makes it non-existent. Okay, but yours?
Think of volume of that.
Yeah.
Million or much more than that.
All right. Well, let's make it up. Okay, at t equals 0, let's suppose the population of these critters is 1,000. Let's go with 1,000. That's reasonable. You got 1,000 Streptococcus bacteria in your throat. Strep is a bacteria thing, right? They give you medicine for it that kills that. I mean, it's bacteria. It's not a virus, right? No. Okay. Anyhow, let's also suppose that the rate of growth, k, is, this thing is in, these guys are increasing at the rate of 5% per hour. Okay? Now, this is compounded continuously, okay? It's not like money in the bank where they're compounding once a day. At the end of one day, they figure out your interest for one day and add it to your principal. Then the next day, they do it again. This is compounded continuously over time, okay? They're always increasing. It's not a discrete function. It's a continuous function. The question we want to answer is, how long will it take these guys to double in population? Okay, that's the question we're going to answer. How long to double? Okay? Here's what I'm going to do. I'm going to solve the differential equation in general, and then we're going to use these specific numbers. Okay? That's what we're going to do. In addition to that, and how many will there be? How many in 24 hours? Okay. Okay. How long to double? And then how many will there be in 24 hours? Okay. Okay. Let's do it. Let's solve the differential equation. We're assuming this is our model for the population growth. dp dt is kp. So dp dt is kp. I'm going to solve it in general, and then we'll apply these specific numbers. This is a differential equation. We solve differential equations at the beginning of the chapter. What do? You separate the variables. Okay. And then what are we going to do to solve this differential equation? What did we do to each side? What did we do? In the beginning of the chapter, we had antiderivatives. Remember that? And we had to solve the differential equation. And I gave you some technique for doing it. You separate the variables, and then you do what to each side? Take the antiderivative. Okay. Now, what's the integral of dp over p? 1 over p dp. What's that integral? That's the natural log. That's right. It's a natural log of the absolute value, but our population is never negative, so we don't need an absolute value here. And that's equal to, what's the integral of k dt, where k is a constant, t is a variable? No, k is a constant. You can take the constant out front. kt, yeah, kt plus c. Okay, that's what we have. Okay, and we're going to solve for c by using the fact that at t equals 0, p is p sub naught. So at t equals 0, p is the initial population. And our problem is going to be 1,000, but I'm going to solve this in general, like I said. So here's what we have. At t equals 0, p is p sub naught. T is equal to 0. Okay. So c is the natural log of p sub naught. Therefore, we have the natural log of p is equal to kt plus the natural log of p sub naught. That's what our c is equal to. Now, what is it I'm trying to do? I'm trying to solve for p, find p at any time t, so that we can solve these other problems. I'm trying to get an equation for the population at any time t. To do that, I'm going to get the two natural logs together. Now, the difference of two natural logs is the natural log of what? What is it? Attaway. That's exactly it. And what I would like to do in order to solve for p is to eliminate the natural log. In order to eliminate the natural log, what should I do here? Yes, raise e. Yes, exactly right. So I'm going to do that. E to the natural log of p over p sub naught is equal to e to the kt.
Is it natural log rate to natural log of e is 1?
Natural log of e is 1. Yeah. E to the natural log of anything is what? What's e to the natural log of x? X. These are inverse functions. If you start with an x and take its natural log and then raise e to that, you'll get x back again. In the same way, if you take the natural log of e to the x, that is also x. Okay? So what's e to the natural log of p over p sub naught?
P over p sub naught.
That's it, exactly. Very nice. Bring the p sub naught on the other side. So we get population at any time t is equal to p sub naught e to the kt. This is our model for population growth. Like I said, it's very crude, it's elementary, It's not good for long-range projections. Why? Because what does this look like, this population growth model? This looks like this. Everybody okay with this? This looks like this. Okay. Starts here at t equals 0, we get p sub naught. This is what you get. That's exponential growth. That's assuming k, okay, is greater than 1, okay? I mean, it's increasing as opposed to a negative, well, it's greater than 0. If it were negative, it would be decreasing, and it would decrease right to 0. This is exponential growth model. You could see why it's not used for any long-range projections, because what happens? It's impossible for any organism to maintain exponential growth over an extended period of time. Why? Because they run out of resources. They run out of room. They run out of oxygen. They run out of food. Okay? Moose in Maine, when populations get too big, what happens to the moose? They get infected with a virus where they go crazy. They start running into things, and they start killing themselves. Okay? This is typical in the natural world. You can't have too many of these things trying to live in the same confined space. Things go bad. Okay? You can't have this exponential growth. What's a better model? We're not going to do right now, but a better model is this one here, where you get this. It's called a logistics function. It starts off exponential growth, but then it levels off to a horizontal asymptote. Okay? This is called the carrying capacity of the environment. Start off exponential, but it levels off. Yes?
Is that also related to the law of diminishing returns?
Yeah, it is, because you get this increasing, and then it slows down. You get it is. It is. That's pretty good. Okay, that's pretty good. That's assuming, of course, the organism exists at all and doesn't just immediately die off, which sometimes can happen. Okay, you get a carrying capacity of the environment determined by oxygen, food, space, whatever the thing happens to be. The difference is, instead of assuming that the rate of growth is a constant times the population, which is what we did, it's the rate of growth is a constant times the difference between the population and the carrying capacity. So as you near the carrying capacity, the rate of growth is slowing down. So, but anyhow, that's called a logistics function. If we had time in the end, we may take a look at this. But right now, we've got this exponential function here. Okay. So let's go back to our strep throat.
So that P equals P naught E KT, E to the KT is what we have to.
Yes, that's what this is our model right here. This is our exponential growth model. And then there are more complicated models. This is just, logistics is pretty reasonable. They are chaotic system models, which is chaos, where it's impossible to predict population at any given time. Small perturbations and initial conditions lead to totally different populations. Okay? All it would take is a cold winter, for example, if you're tracking wolves in Yellowstone or something like that. And you have no control over this. These random events, minor perturbations can lead to major changes in the outcome. These are chaotic systems. Population growth models are amazing stuff. Anyhow, so back to our strep throat. Where do we start with? We had initial population of 1,000. We had K is increasing at 5% per hour. So here's what we have. Our population at any given time is 1,000 e to the 0.05 t. Okay. What do we want to know? We want to know how long to double. Well, let's see. What do we want to do? We want to find the time it takes the population to go to 2,000. Okay, we're going to find the doubling time. Now, would it make any difference in this model if we're going from 1,000 to 2,000 or from 5 to 10 or from 1 billion to 2 billion. Would it make any difference at all? No, it would make zero difference because that ratio is 2. Divide by 1,000. You get 2. Okay. Theoretically, it makes no difference. In the real world, it may make a difference, okay? But anyhow, theoretically, it doesn't. We want to solve for t. What should we do to both sides?
Natural rule.
You bet. Okay. Natural log of 2 is equal to natural log of e to the 0.05t. The natural log of e to the 0.05t is 0.05t. We want to solve for t. Okay. 0.05 is 1/20th. I'm going to multiply both sides by 20. Okay. So the time it takes these guys to double, increasing at 5% per hour, is 20 natural log 2 hours. Can somebody do that out for me on a calculator? 20 natural log 2.
13.8.
What is it?
It's 13.863.
So in 13.86, right? Yeah, 13.9 hours. Thank you. It would take to double at 5% per hour. And the reason it's not 20 hours, okay, you might think, geez, why wouldn't it be 20? Is because it's compounded continuously, okay? It's continuous compound. Not every hour, not every minute, not every second, but continuous compounding, okay? Banks could give you on your money a continuous compounding interest, but it would be so confusing for people that they say, forget it. They compound it. They have daily interest where they compound it daily. Do they have hourly compounding? I don't put my money in a bank. What's that?
That'd have to be a pretty stupid bank.
Yeah, well,
Pay out so much money on it. Like
no, yeah, but it wouldn't be that much. It seems like, geez, my money would go to infinity really quickly, but it doesn't, okay?
It'd be really low.
Well, it's better than compounding hourly, but not by much, okay?
I can guarantee if there was a bank that I could put $1,000 in, and 13 hours later it's $2,000, I would put all my money in.
Yeah, yeah, 13 hours, that's true. Yeah, well, they're not going to compound at a 5% per hour. They'll do it at 5% per year compounded continuously, which is why the banks give you two rates of interest. They give you an APR, an annual percentage rate. It's not anywhere close to 5%. It's like, I don't know what it is now. It's like 0.5%. Or I don't even know what it is. It's like nothing. Yeah, I know. It's like negligible. They don't give any interest anymore. They used to give like 4 or 5% interest a year. Okay, but now it doesn't even come close.
So I gotta go to a credit union.
Is that what? Yeah, really? Credit union? All right. Okay, but here's the deal. You got an APR. That's what's like 4% per year, let's say. Then you got an effective. Okay, it's called their yield. It's their effective rate of interest because it is compounded daily, okay, which means they take 1/365th of your money, find the interest over that, and that's added to your principal for the next day's interest, which is a little teeny tiny bit more than what it was the day before. That's compounding, okay? So what happens to that, say, I don't know if I said 4 or 5%, whatever, 5% compounded daily turns out to be 5.23%. That's the effective yield of that. Compounding continuously. You get that little bit extra. Okay, it's not a whole bunch extra, but it is something extra. But banks don't even, they don't even do that anymore. Okay, anyhow. Okay, how long to double? What else did I want to know?
24 hours.
How many of these in 24 hours? Well, let's see. In 24 hours, how many bacteria do we have? Well, we want to know the population in 24 hours. Okay. By the way, before we do that, how long would this population take to quadruple?
Should it take roughly 28 hours?
Exactly. It would be. It'd be 27.8 hours. It'd be twice this. Because quadrupling time is doubling the doubling time, and doubling time is 13.9. So it doubles the double, which is going to be twice this. 27.8, roughly 14 hours.
To sort of get that
24.
rate figured out, that does account for the compounding nature.
Yes, it
of
does.
bacteria.
Yes, it does. Good deal. Okay, so in 24 hours, How many of these strep germs do you have in your, I don't know, it's 0.05, I need someone to do 1,000 times e to the 0.05 times 24.
3,320.
Whoa, what is it?
3,320.
Oh, thanks. Okay. 3,320. So they've more than tripled in the 24 hours, okay? And how many would there be, and let's say if they went untreated for a month? Let's say you went untreated for a month, okay? 30 days, 24 hours a day, okay? 30 days times 24, and so you've got population would be 1,000, E 0.05. You got 30 days times 24 hours a day.
100,000?
How much?
Like around 100,000?
I have no idea. It's going to be big though, because exponential growth is just that. What is it?
About 4.3 times 10 to the 18.
Times 10 to the 18th? That is so cool. Times 10 to the 18th. How many cells do you have in your body? Not this many, I don't. Although maybe you do. I'm not sure how many cells you have. I have more cells than most people, but
It's like a perspective thing.
brain cells is what I was talking about. What's that?
Typically, you have more bacteria in your intestine than there are grains of sand on all the beaches in the world.
E. coli and the like, yeah. But 4.3 times 10 to the 18th, we're talking about an enormous number. We're talking beyond trillions and quadrillions and quintillions. And I don't know what we're talking about.
About 10 to the 13th human cells.
Oh, really? 10 to the 13th
And
human
then,
cells.
And then in comparison, the bacteria cells are 10 to the 14th in the human body.
Oh, wait, say that again.
Yeah.
We have 10 to the 13th
Human cells.
human cells, and there are 10 to the 14th bacteria.
Yeah.
So I have more bacteria per cell than I have cells.
Yeah.
In other words, I'm bacteria ridden. I should just go home and curl up in bed and die, is what you say. Wow, that is stunning. What an amazing, that's stunning. That's stunning. But 10 to the 18th dwarfs both those numbers, okay? That's if left unchecked, but what happens? Before they reach that population, they kill their host, okay? And then the host is dead. And then I don't know what happens to strep germs after that. How do they're not airborne. I don't know. How do they go from one host to another? Is it airborne?
Strep
If somebody
is
strep
saliva.
saliva? So somebody has to spit on you? All right. I better not. No, I don't have strep though. So I was going to say. I know when I speak. We went to a play in Springfield, Hamlet, and we were like in the first row, and that guy enunciated and was loud. And I was soaked with his spit at the end of that play. It was unbelievable. But anyhow, hope he had nothing bad. But, okay, that's population growth. I would give you a problem like this, expecting you to know that P equals P sub naught e to the KT. I would give you that K and P and ask these kinds of questions. There's one more thing we have to do, and that's radioactive decay.
Does that one also use natural log?
Yeah, it's the same. It's basically the same. I'm going to derive it, but everything is virtually identical. In radioactive decay, Q is the amount of radioactive material. dQ dt is a negative KQ. Okay. It's a rate of decay now. It's decreasing over time, and it's decreasing at a rate that's proportional to the amount of radioactive material. Okay, same idea as before. What do you get for a graph? Now, these models are very accurate, okay, as opposed to the population growth models, because what you have is this. You have this kind of a thing happening here. Whoa! Okay? And these are very accurate. In the 1950s, the scientists who used this radioactive decay model, okay, for carbon-14 dating of fossils and the like, won a Nobel Prize for that by using this very technique, okay? Because what happens is when an organism, let's say a dinosaur is alive and eating plants, it's creating carbon, and part of that carbon is carbon-14, the radioactive carbon. When that animal dies, it doesn't produce any more carbon. The radioactive carbon-14, decays over time. It has a certain half-life of like 5,500 years. So So if you find a bone with so much carbon-14, you know how long that bone's been sitting there, because it loses that carbon-14 over time. And you can predict the date of that bone, and that's what happened in the 50s. And that's what they were able to accurately predict the age of dinosaurs, yes.
How do you know how much carbon-14 is supposed to be there to start?
It's a certain percentage of carbon. So if you've got a bone that weighs 10 kilograms, and the amount of carbon in that bone should be, let's say, 1 kilogram, of that, initially, maybe 3% of that was carbon-14. Now you find the bone, and now it's only 1% or 0.5%. That decay in carbon-14 enables you to predict that bone.
So that's pretty constant, like the amount of...
Yes, it is. Yes, it is. Yes, it is. Yeah. Then they've got even better techniques, because carbon-14, what did they use now? Radioactive iodine is used. And
The carbon-14 issue is that typically it stops being ingested, but the environment could affect it.
that's possible. Yeah, I know there were some problems with that. Now they use different techniques when they're really accurate with predicting. Radioactive iodine, for some reason, comes to mind. I'm not sure what the half-life of radioactive iodine is. Does anybody know? Nobody knows? Then I'll tell you what it is. It's 57,260. No. Okay, so let's do it's the same idea as what we've just been doing, okay, except now it's decreasing over time. We're going to solve the differential equation, and at t equals 0, q is q sub naught. So what do you get? You get dq over q is equal to negative k dt. Integrate each side. Natural log of q is equal to negative kt plus c. And again, at t equals 0, q is q sub naught. So you get the natural log of q sub naught is equal to, this is 0, c. So, natural log of q is equal to negative kt plus natural log of q sub naught. Subtract this natural log. Okay. Difference of the two logs is the log of the quotient. We want to get rid of the natural log, raise e to that exponent. E to the natural log of anything is that anything. And we get the formula for the amount of radioactive material at any given time is q sub naught e to the negative kt. Okay. Let's do a half-life thing, okay? Let's do a half-life. Let's suppose that q sub naught is equal to 10 kilograms. Okay. And let's suppose you know that this carbon-14...
Plutonium-238 is 5,000 years.
That's 5,000 years? What's the carbon-14? Is that... I said 5,000. I thought it was...
It's very long. That's why they can use it on like dinosaur bones and stuff.
It's longer than 5,000 then, huh? Maybe I was getting confused there.
Just know the plutonium thing is poison.
Is that right? Oh, yeah. Okay. So let's suppose we have 10 kilograms of plutonium. What's that? PU?
Yeah, PU.
238?
Yep.
So what do you write that? Like this or something?
Yeah, because you write at the top because it's an isotope.
Yeah. Okay. Okay, that's our initial amount. Let's suppose, here's what we know. Instead of knowing how fast this thing is decaying, let's suppose we know after so many years, after t equals 10,000 years, Q now is equal to 8 kilograms. So here's what we know. We got this plutonium-238, radioactive plutonium. We have 10 kilograms of this thing, okay? We know that this thing has been in that state for 10,000 years for some reason, because it was found with the dinosaur bones who we aged 10,000 years. I don't know. Okay? And now there's only 8 kilograms. We know that 10 kilograms was there originally, and now it's down to 8 in 10,000 years. What we want to do is determine what is the half-life of this plutonium-238. Okay? Now, obviously, I'm making up these numbers, so I don't quote me on any of these numbers. Okay? So we want to find the half-life. We don't know the rate of decay. We're going to have to find the rate of decay first, and then we can find the half-life. So let's do it. So here's what we know. Q is equal to 10 e to the negative kt. Okay. Q sub naught, 10. We do know after 10,000 years, Q is now 8 kilograms. Okay. What we're doing here is solving for the rate of decay. Divide by 10. Take the natural log of each side. The natural log of e to that exponent is that exponent. Okay. K. All right. Here we go. K. Everybody else set with this? Okay. How are we doing, all right? Everybody okay? Okay. The rate of decay, K, is equal to the natural log of 0.8 over a negative 10,000. Now, please note, this is going to be a positive number because the natural log of anything less than 1 is negative. So, what do we get for K here?
I would counter 2.2 times 10 to the minus 5th.
Sounds good to me. Okay. Okay. Is that about right? You agree with that? All right, then we know that's right on. All righty. So that's K. So here's what we have. Q is equal to Q sub naught e to the negative kt. We know that Q is equal to, in this case, 10 kilograms e to the negative 2.2 times 10 to the negative 5th t. We want to find half-life. Bless you. Okay. So, Q equals 5. Good call. Put a 5 in for Q. We want to solve for T. Divide by 10, you get 1/2. Does it matter if we're going from 10 kilograms to 5, or from 100 kilograms to 50, or from 1 billion kilograms to 500 million kilograms? It doesn't matter. Okay? That half-life will be constant. Okay? The same way that doubling time with the bacteria are going to be constant under our exponential growth model. That's equal to e to the negative 2.2 times 10 to the negative 15. Take the natural log of each side. Natural log of e to anything is that anything. So, half-life is approximately equal to natural log of 1/2 over negative 2.2 times 10 to the negative 5th, which is approximately equal to, I don't know, 10,000 years it lost, I don't know what it is. Oh, I don't know what the number is here. I have no idea. 50,000, I'll guess. I'm taking a stab at it.
30,000 years.
It sounds good. Everybody, we have agreement on that? Let's see what Lewis
What are we
says.
rounding it to?
Nearest 10,000.
32,000 years.
No, that's the nearest 1,000.
See,
Sorry, Sam.
it's all good.
30,000 years. All right. Okay. Any questions on that? That's a radioactive decay model, okay? That's the derivation, that's what it's used for. So, on the test, you're going to have one of two problems on that section, either a population growth model or a radioactive decay model, okay? And I would expect you to be able to do what we just did, okay? What we're going to do, yes?
Are you going to give us the formulas or no?
No, because I expect you to know those two formulas. This is this one, and the population is the same one, except it's not a negative. I don't think that's too bad.
It's not what, is it?
It's not negative. It's just KT.
Oh, it's just the same.
Yeah, that's the only thing. Okay, so for Thursday, here's what we're doing. I'm going to give you a sample test. Okay? You're going to work on it. It's not multiple choice. It just gives you an idea of the kinds of problems you're going to see in the test. Okay? We're going to go over that. And then what we're going to do is take a look at the lab, and we'll take a look at what I expect you to do. Now, the Mathematica labs, I would expect you to have Mathematica on your machine. It's a free download from the stick.edu/math website. You have to follow their instructions, and you can get Mathematica for free for 1 year, okay? You're going to take the lab no, this is not a lab that I've written. This is one that Professor Benelli has written. So it's one of these labs where what's your name, what's your favorite color, things like this. It's okay. It's okay. It's all good.
Is it the same one we did last semester?
No, that's count 1. Oh, no, this is count 2.
Yeah.
No, you're going to have the better lab. Maybe I've written these. I don't know who's written these. I have no idea what this lab first lab is. I really don't know what it is. I was thinking of the count 1 lab. Yeah, but I don't know what this looks like. So we'll go over Thursday. But the bottom line is, I don't want people to freak out over this Mathematica if you've never used Mathematica thing. You download what in my Dropbox. It's a .nv file. It's a Mathematica notebook file. You take that. When you double click on it, it'll automatically open up Mathematica. And then what you want to do, you want to read through. I'm going to go over this on Thursday. And then you can select a piece of the code from an input cell and put it down here, and then do something. You got to change a couple parameters, maybe add a couple things. It's not complicated. It's not like you're going to have to do a whole bunch of coding or anything like that. It's just a few changes. It's pretty simple.
It's on WebAssign, right?
They're on WebAssign, but I always have problems with WebAssign. I must not be doing something right. I put the labs on WebAssign. They're there. I put student access, enable it, saved. I can see them. I can download them. They download to my machine, fine. As soon as a student tries to do it, it says you don't have access to it. I don't know why it does that. So what I've done instead, I've emailed you a link to my Dropbox, where you have to put that link in to the URL into your browser as one line. Make sure you make it one line. Or else I guess I could do a whole bunch of stuff, so you don't have to do it as one line. But do it as one line, and you get those labs. If you have problems doing that, email me. I'll send you all 4 labs. You guys have 4 labs. I'll send you the 4 labs just as an attachment in an email. The point is, it's not that bad. It's not going to be complicated. It's not really that bad. I don't want anybody stressing out over the fact that the labs are mathematical labs and you've never used Mathematica in your whole life. Okay? So I don't want anybody stressing out. Okay, is anybody stressing? You're stressing. Is that what that meant?
No.
Oh, okay.
I thought I heard you say we get extra credit for coming in today, right?
Did you
I heard that.
I think because of the bad weather, I mean, this small class.
Listen, you know what your grade is. It's blah, 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 blah. And there's no room there for, oh, he came in. But there is room for participating and being here. You're right. So you do. Louis, you know you always get that.
Listen.
I would, for you, your average, if you get an average of like 72, that's probably an A.
That's easy. That's easy.
All right.
Without the extra credit.
Yeah. All right. See you Thursday.
Can you give me the Practice test.
Oh, the practice, I have one copy, you guys,
I won't be here until New Year's Day.
oh, yes. I'm gonna make copies of it right now, so
So the mathematical, the one we downloaded last year.
it's still good. It's still good. It may run out, it's good for 1 year, but if you did it in the fall, it still should be good.
I think it's like 5730 is the half-life of carbon 14.
What is it?
I looked up, it was like 5,730.
5,000 something.
You're pretty close, yeah.
Was that close or what though?
Do you have the practice there with you or no?
I do have it with me. I have to make copies of it though. I made one copy because I wasn't thinking that people would want me to go over there, way over there and make copies of it.
I need to.
Yeah,
I need to tap it.
I'm gonna make copies of it.
I asked her, "Are you gonna do that?" No, I don't want to put that. She's like, "No, that's impossible."
Oh, no, you don't want to wait. That's what the thing is on Lois. You just don't want to wait for them.
Looking out for you.
Yeah, that's true. You got-
He said if you put in the wrong number.
Oh, it's still recording. Oh, I can probably get the recording.